Okay, guys, we are going to try this problem. You are attempting to row directly across a body of water in your rowboat to a dock that is directly across from you. Okay, so there's a dock somewhere, and you're over here, and you're going to point your boat in that direction. Okay. And you want to get to the dock that's right here. Okay. It says your paddling speed relative to still water, like if you were on a pond. Okay, in other words, you're able to go at a certain speed, 5.0 meters per second. Okay, so you're going to use your oars and you're going to get yourself across there. If you were on a pond, you'd go directly across to the dock. You'd get there. End of story. Okay, but now assume that you're on a stream that flows east at 3 meters per second. So I'm going to draw another thing. You're still going for the dock over here, right? You're starting here, okay? But it says here the stream flows east at 3 meters per second. So let's say, the stream has some kind of current. The current is 3.0 meters per second. So it's downstream. Okay, that's east. All right. You still want a boat to go across, okay? But if you head straight across at 5 meters per second, you're not going to end up there. The river's going to carry you downstream, so you're going to end up down here somewhere. Okay? That's not what we want. What do we have to do? Well, we have to set our course to compensate for the downward flow. And what that means is what we want is our direction and speed plus the direction and speed of the current to add up to the result that we want, which is that we want to go straight across. This is what we want to do. So I'm calling it our resultant vector. That's where we want to end up. But we know the vector for the river, and we know that it is 3 meters per second downstream. Okay, so let's draw it here. The reason why I'm going to draw it here will become clear in a second. Okay, here's the velocity of the water, okay, which is 3 meters per second. Okay, because I know I'm going to have to head upstream at some angle to make it work. I know that I can go 5 meters per second if I head upstream and I add that in such a way that my vector plus the river vector, the water vector, right, will add up to what I want to do, which is go east. So I've got a triangle now, and I've got a right triangle. So I'm going to figure out which angle I'm going to head upstream at. Well, to do that, I'm going to find the angle that's in my triangle first, my reference angle. Okay. So now how am I going to do that? Well, I have an angle that I want to find, and I have my opposite side I know the length of. It's 3 meters per second, so this vector represents speed, and I know my hypotenuse. So I'm going to find the angle right away. Tan alpha is 3 meters per second divided by 5 meters per second. Okay, so alpha is tan negative 1 of 3/5. So what does that make alpha come out to be? Use your calculator. 3/5. 30.964 degrees. Okay, so I know what alpha is going to be. That means if I want to find theta, I know that alpha and theta add up to 90. So I'm going to say theta is 90 minus 30.94. Oops. There you go. And that means that theta is just a little below 60. 59.036 degrees. Okay, so I'm going to be heading upstream. We know downstream is east, so upstream would be northwest, right? So I'm going to be heading, but I would say at an angle to the, at a northwest at this angle. Okay, you could say upstream this angle, we should say in either case, to the shore. So that we know that the shore is our reference location for the angle. Okay, so that's the angle. Now, how fast am I going to actually be going? So we want to find VR. So VR squared equals the water squared plus my rowing speed squared. So VR equals the square root of 9 plus 25. So 9 and 25 is 34. Square root of 34. And that's going to be meters per second also. If we want to figure that out with a numerical number to see where it fits in with our other ones, the square root of 34 equals 5.831 meters per second. So what mistake did Ms. Felder just make? I want you to look at what I made, and if you haven't already figured it out, figure it out. Okay? I mistakenly acted like the resultant was the hypotenuse. Okay? And so when I got my answer, 5.831, I thought, wait a minute. There's a problem here. This vector cannot be longer than the hypotenuse. Okay? So that makes me know that I did that part wrong. Okay? So I have to go back and I have to say, wait a minute. It's actually 5 squared is the hypotenuse equals 3 squared plus VR squared. So 5 squared minus 3 squared equals my resultant velocity squared. So VR is going to equal the square root of 25 minus 9. Okay, well, 25 minus 9 is 16. So the square root of 16, which equals 4. So the resultant velocity, and we could have figured that out now, couldn't we have, right? It's a 3, 4, 5 right triangle, is 4 meters per second. So what I actually travel across the river is 4 meters per second straight across. In order to do that, I have to row 5 meters per second at an angle of 59 degrees, 0.036 from the shore upstream. Okay, so there you have that one. Okay, now we're going to try another example. This is an airplane in the wind example. Okay, an airplane has an airspeed of 500 kilometers per hour at a true bearing of 80 degrees. Let's go back, that true bearing and airspeed. Let's go look down here. Airspeed is speed relative to still air, the way the pilot is setting the plane. Okay, so we know that the plane can go 500 kilometers per hour, and we know that the angle of the plane is 80 degrees, and that's a true bearing, so that's starting north measured clockwise. Okay, so I'm going to draw a picture. And that's what the plane is doing. So 80 degrees from clockwise. So he's actually heading pretty much this way. This angle is 80. That makes this angle 10. Always good to know. And we know that he's going 500 kph, kilometers per hour. Now the velocity of the wind is 60 kilometers per hour at a true bearing of 300 degrees. True bearing of 3. So if we go with true bearings and we go all the way around, we've got to 270. So actually the airplane is going at a the wind is going at a 30 degree angle from the negative x-axis. But it's only going 60 kilometers per hour. Okay, so actually I should have drawn the wind a lot. 500. I should have drawn the wind a lot less because it's not really this long. But the point is, when we move this to the tip of this, okay, we can see that it's pushing the airplane up, okay? So our result is going to be something that is between them, right? Wherever you get when you would add, it would be more like this, right? I'm trying to do the tip to tail method by just sketching out what it would look like. So yeah, so my resultant would be here. But we know this scale is a little off because I made 60 a lot closer to 500 than I should have. But the point is we're going to be going up in that direction in between. So the first question says, find the velocity of the plane relative to ground. Now that says velocity. That means we want the whole vector. And that means we can either give a magnitude and direction, but that seems to be what they're trying to tell us. Speed is the magnitude of velocity, and direction is here. So we're going to get the magnitude and direction later. To find the velocity, what we should do is use vectors, component vectors, okay? So let's do that, okay? We have the airplane. Okay, so the airplane is over here. It has an x component and a y component. We could use 10 degrees because that makes it pretty easy. The x is positive. So we're going to say 500 cosine 10 degrees. And the y is positive also. So we're going to say 500 sine 10 degrees. Okay. Then we're going to have the velocity of the wind. Now this is a vector, so we label it a vector. Velocity of the wind. Okay, that's going to be in the negative x direction, 60 cos 30. And the positive y direction, 60 sine 30. Okay, now we're going to add them together to get the velocity of the plane with respect to the ground. In other words, what is it actually doing when we're looking up at it? Okay, well, velocity plane with respect to the ground, I'll just say. Okay, so I'm going to have to add these. 500 cosine 10 minus 60 cos 30. And then 500 sine 10 plus 60 sine 30. And I can do this with my calculator. So 500 cosine 10 minus 60 cosine 30. Okay, that's going to give us 440.442 kilometers per hour. Sometimes I just put the kph on the outside. You definitely want that. And then here it's 500 sine 10 degrees plus 60 cosine, 60 sine of 30. Okay, so that gives me 116.824 kph. And they're both positive, okay, which makes sense because it should end up in the first quadrant. Okay, so now I've gotten the answer to the first question, A. B says the speed of the plane relative to the ground. Well, the speed is just the length of the vector, the magnitude. So we know the magnitude of the velocity is going to be the square root of 440.442 squared plus 116.824 squared. Okay, so we can calculate that. By just doing it. So, and I'm going to use the stored numbers in my calculator. So I'm squaring the previous answer that I got, and then I'm adding that to the even previous answer that I got. And the square of that too. Take the square root of the whole thing. What I get is 455.672 kilometers per hour. That's the magnitude of it. And the angle, we'll want this angle here. Let's use the red so we can see it. We'll want this angle here. Okay, and so we'll think about this triangle, right? The cosine is going to give us the y, and the sine is going to give us the x. So, or we want the tangent actually, because we already have the x and the y. So the tangent of the angle is the y, which is 116.824, divided by the x, which is 440.442. Now I'm going to use the original numbers to find theta with the inverse tangent. Okay, divided by, sorry, I put something in the wrong order, so now I have to insert the correct number, which is 116. And we're dividing those two. Enter. All right, so what I got for that is 14.855 degrees. And that seems reasonable. It was 10. It's been put up a little bit, almost another 5 degrees. And that is from, we're going to say, this is an airspeed, so it says as a true bearing. Okay, so if we found, so this is not actually what they want. This is our alpha, 14.855. But we need to actually have it as a true bearing, which means relative. We need to go from north down to that vector. Okay, so all we have to do there is we have to do 90 degrees minus 14.855 to get our angle. And our angle will be 90 minus that 75.145. True bearing. So, I mean, I try to model, right, my work, and as you can see, I make mistakes along the way. I think one way, and then I think, oh, wait a minute, they're asking me for the other, or I by accident use the Pythagorean theorem wrong. Okay, this is what the process of doing math is. It's drawing, it's trying to interpret it, it's then figuring out, okay, components are easiest to do here. They want it in component form anyway, even though they don't quite say that, but they, we want to find the speed and direction. Well, we're going to get that from the component form. Okay, and so we've got our answers now, and you're going to try your homework tonight.